In lab, you guys smashed a couple carts together and we watched the results of what happened in that collision. Now, what you were investigating is what we call the law of conservation of momentum, and before we jump into that, I want to make sure that you know two things. Momentum is mass times velocity, so P equals mv, and also momentum is a vector quantity. That's important. Direction matters. It is not the same thing. 8 kilogram meters per second is not the same thing as negative 8 kilogram meters per second. One of those is in a positive direction, one of those is in a negative direction, and that does matter when we're talking about momentum. So, in lab, we took a cart that was at rest, and we put it right here, and we had another cart that was over here, and we gave this one a shove. Okay. Now what happened as a result of that is a collision, and these two carts interacted in some way. So a little bit while later we had a collision where these two things actually hit. Now this instant in time actually has a duration. It's not instantaneous. It has an impulse, right? A force acts over time and it causes momentum to change. That's what you looked at in the last unit. So at this instant you actually have a force here. This is the force from 1, and then you have a force back on this cart, the force from 2, where this is cart 1 and this is cart 2. And Newton's third law tells us those two things are equal in size and opposite in direction. We put that together with the fact that these were in contact for the same amount of time, and we see that F1 delta t is going to be exactly the opposite of F2 delta t, which tells us the impulse that these things feel are equal and opposite, which means the change in momentum of this one is equal to the negative change in momentum of that one. Okay? Now that's a big, long, convoluted way of saying the momentum can transfer from one thing to another, but the total amount of momentum is going to be the same, because if I take delta p plus this negative delta p, I get 0. Okay? So the total change in momentum is 0, which is really what the law of conservation of momentum says. It says in a closed isolated system, what we know is momentum is conserved. What that really means is the momentum before a collision is equal to the momentum after a collision, but you have to be careful about this closed and isolated thing. Okay? Closed is exactly what it sounds like. If something is closed, nothing gets in, nothing gets out. So no mass is gained or lost. Usually this is not an issue. The only time you have to be careful with this is if we have a rocket problem where it expels hot gases out of the rocket. If your system is the rocket, once the gases leave, that means your system isn't closed and the law of conservation of momentum doesn't apply. The isolated part means that you're not going to have anything coming in from the outside and changing it. What I mean by that is no outside forces act. Okay, friction is an outside force. If you have friction coming into this, then you're going to have an outside force that's changing it. Gravity could be an outside force. If gravity is unbalanced, it can change this. So you have to be careful when you define your system. Is it closed? Is it isolated? And if it's not, we've got to take account into those things that could change it. So when you had in lab, you had the two carts that smash into each other. You have this one here and this one here, and this is your system. Your system is composed of these two carts. Is this thing closed and is it isolated? Well, as long as no forces act and friction is small enough that we can ignore it, then that's okay. Gravity is here, but it's exactly balanced by the normal force, so the net force is 0. So we have a net 0 force, which means it's isolated, and no mass is going to be gained or lost as long as everything remains in the cart. So yes, this is a closed, isolated system. Now what happened was this cart's in motion, right? Because we gave it a push, so that was an outside force. That was where our momentum originated from that outside force. So we gave this cart a push, and it's moving this way with some velocity. This is cart 1, and it has an initial velocity of 1. Okay? Or maybe I'll say this A. This is cart A with initial velocity A. This over here is cart B, and it has initial velocity b, and then we have a collision. We don't really care about the collision. What we want to know is what happens after the collision. So I'm going to draw before and after pictures, and I'm going to draw them side by side. This is a good way to keep track of all the information you know in a problem. Before and after pictures are a good way to organize your data. So before anything had happened, and by this I mean before the collision, before the interaction, before whatever happened. Okay, so not before we pushed it, but before we had an interaction. We had a cart at rest, and we had a cart in motion. Okay? So I have an initial velocity this way, and I have a velocity equal to 0. This is cart A, say. This is cart B. Now, if I want to know about the momentum before the collision, I'm going to take the velocity of cart A times the mass of cart A to start with. So velocity of A initial times momentum of A, or mass of A initial, and that's going to give me the momentum of A at the beginning. And over here I'm going to have the velocity of cart B times the mass of cart B, and again these are initial because this is before the collision, and I can multiply those and I get the momentum of cart B. Okay, initially. Now the total momentum of my system is the sum of these things. You have to keep in mind that direction matters. So if this cart hadn't had an initial velocity of 0, if it had an initial velocity of that direction, then one of these two momentums has to be negative because one of them's to the left and one of them's to the right. So you can actually add up two momenta to 0. Just like you can have two forces that act in opposite directions, the net force can be 0, the net momentum can also be 0. So what I have over here is the net momentum, or the total momentum at the beginning is equal to the momentum of A at the beginning plus the momentum of B at the beginning. Now the law of conservation of momentum, all it says is that after these things hit, we still have that same momentum. So if this cart now is moving this direction, that means its momentum increased because it used to have 0 momentum and now it's actually moving. The only way that can happen is if this thing's momentum here decreased, and it could have gone to 0, this cart could have stopped, it could have gone negative in reverse direction, but the momentum over here has to remain the same. So what I have over here, this is still cart A, this is still cart B, but now their velocities are going to be different. So the velocity of cart A at the end times the mass of cart A at the end is its momentum, final momentum. This is momentum cart B, so velocity cart B, mass cart B is its final momentum, and if I add those two things up, I get the final momentum is equal to, or the total final momentum is equal to the momentum of A plus the momentum of B after the collision. And this is the law of conservation of momentum. This tells me that the net initial momentum is the net final momentum. So if I know enough information, I'm able to use the law of conservation of momentum to figure out how fast these two carts are going to be going, if they're stuck together, or if I know which one, what happened to one, I can figure out what happened to the other. This is a very powerful law, and it works as long as you know you have a closed and isolated system. If you have outside forces, it changes it.